Hello friends, this video on Equilibrium Part 2 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched Part 1. So, there are various types of dynamic equilibriums. The first is a physical one, and we'll talk about the subtypes of physical equilibrium. That is solid liquid equilibrium. In solid liquid equilibrium, we have solid and we have liquid. They are in equilibrium. Then we have liquid vapor equilibrium. So you see, there's a liquid vapor equilibrium, and then we have solid vapor equilibrium. That is this equilibrium. So there's solid and the vapors. There's my ice. There's my water. And then we have dissolution of solids and liquid, as we have talked about. You dissolve sugar or salt in the glass of water. That is dissolution of solids in the liquid. And then we have something called dissolution of gas and liquid. You must have seen the Coke bottle. The moment you open up, you'll see the bubbles. If you see these bubbles here, right? The bubbles comes up. Why it comes up? Because this gas was already dissolved in this liquid. The moment you open, the pressure decreased and it came out. We will discuss about this, how it happened. But we have seen here that the gases are dissolved in the liquid. Right? The gases are dissolved in the liquid. And then we have something called chemical equilibrium, where we have two chemicals combined to form C and D. This is F, or you can use this fashion, where you can say that A and B are in equilibrium with C and D. We'll discuss more about this when we see the two reactants reacting with products in their equilibrium. And the types of chemical reaction we have is the normal chemical reactions, or ionization, or the hydrolyzation of salt. So we'll discuss all these things in the next chapter. Let me repeat once again, because this is the basic structure of the chapter. Solid liquid equilibrium. So when we say that the solid, for example, ice is in equilibrium with what? How you keep this ice and leave it for some time, it melts, right? There's equilibrium here. Then we have called liquid vapor equilibrium. We have water vapor, and the water, they are in equilibrium sometimes when you boil it. Or solid vapor equilibrium also we have in some case for sublimate substance. And then we have a dissolution of solid and liquid. We have solid like sodium chloride, sugar, we dissolve in liquids, water. We have dissolution of gas and liquid. We see the Coke or the soda we use, it has bubbles. That is nothing but gases to dissolve in the liquid. And then we'll have chemical reactions. We'll discuss three kinds of chemical reactions. Let's talk about the dynamic physical equilibrium first. As I told, in physical equilibrium, there is no change of chemical property. Please note, there is no change of chemical property. That is the basic difference between the physical equilibrium and chemical equilibrium. Physical equilibrium, we don't change the chemical property, but in chemical equilibrium, we do change. For example, when you talk about, let's suppose I have HCl, it gives H plus Cl minus ions, right? So this here we are changing the chemical property. This won't be equilibrium because it's a very strong acid. We'll discuss all those things in the next few slides. We'll talk about which kind of chemicals goes for this chemical equilibrium. I think NH3 is one example, good example of chemical substance which goes for chemical equilibrium. Anyway, we'll discuss those things later. So we have something called phase transformation happens here, right? For example, solid to liquid, or we have liquid to gas, this example, or we have solid to gas. Also, we have, in the same case, we have cases where we dissolve solid or gas in liquid. Please note, we dissolve only in liquid. We never talk about dissolving solid in gas, or we never talk about dissolving gas in solid. It's always we dissolve, because we talk about dissolving, that means you talk about liquid. And what you can't dissolve liquid in a liquid, right? That's nothing, that's truly insane to say. Liquid in a liquid is nothing. You can't dissolve it, it'll be a mixture. But when you talk about dissolving solid in liquid or dissolving gas in liquid, then we have this physical equilibrium comes into play. So when you dissolve solid in liquid, we have one example of dissolving sugar crystals or salt and water. When you talk about dissolving gas in liquid, the good example is the Coca-Cola or the soda. When you open it, you will see the gas bubbles because the gas are dissolved in the liquids. So we'll discuss all these things in a detailed manner. See, when you talk about solid liquid equilibrium, we have a concept of melting point. What is that? The definition says, for any pure substance, please note, for pure substance at atmospheric pressure, the temperature at which my solid and liquid phases are at equilibrium, that is called my melting point. And you know, in this case, if you see, I have ice here and this melts, this gets water, they are in equilibrium actually. Some of the molecules from this surface of the ice comes out and becomes water, and some of the molecules from this water goes and becomes ice. And that's dynamic in nature, it keeps happening. So if you see, the observation we have is both the process of melting and cooling are happening simultaneously, and they occur at the same time. They happen simultaneously and they occur at the same time. So when you talk about the melting point, the word equilibrium comes into picture, because the melting point is nothing but the temperature at which the pure substance at 1 atm pressure is at, in that case, my solid phase and the liquid phase are in equilibrium. That temperature is called melting point. So let's talk about the liquid vapor equilibrium. So let's suppose we have this jar in the water, and we give little bit of heat in here, little bit of heat, very little. So what will happen is this will evaporate little bit, and you see the molecules will go up, more molecules will go up. So if you see, the molecules are going up. After some time, if you see, the pressure will go up here, and now if you see, the molecules are going up and coming down. It's happening in both direction. So you saw what happened. So I'll just repeat once again. Earlier, with heat, the molecules were just going up, and then with pressure build up, the pressure increased here, and after some time, you see, the molecules started going up and down, both at the same rate in the same direction. So that's why if you see, the rate of evaporation here is equal to rate of condensation, right? And that's what you have equilibrium in this case. Rate of evaporation equal to rate of condensation. Another example you can have is, you can have this kind of jar, three-dimensional jar actually, and put some calcium chloride in this and hydrous. What this calcium chloride will do, it will take out all the water molecules from this air here. So the air will become very dry. Once the air is dried and the pressure is same here, what you do is you add some dish of water here, just dish of water, don't even need to have heat. The normal evaporation process will take, and the water from here will go to this area, right? Now the water level will be less and the vapor pressure will be created. If you see, the mercury level will go down, and then after some time it will attain a fixed level. It won't go down further. It won't go down further. This is the maximum. It won't go down further. So at this point, what will happen is, the water molecules, since it was going in this direction now what will happen is, some of them will start coming in this direction also. So if you see, there is equilibrium here. Some are going, some are coming. And then you see the level of the water, the mercury level is constant. And here also, if you see, it's not that it is stopped. It's not that it's stopped now. It is dynamic. The water molecules are going, mixing, getting mixed in the air, and water molecules from the air is coming, getting cooled down and getting into water stage. So if you see, this is my liquid and this is my vapor. There is an equilibrium between liquid and vapor. Here also we had this equilibrium between liquid and vapor. The molecules keeps right. And if you see, the same experiment which we have, this one is repeated with methyl alcohol or acetone or ether. It is observed that different liquids will have different equilibrium vapor pressure at same temperature. So if you do this with methyl alcohol, you won't see that the mercury will be here. It will be somewhere different, somewhere up or down. That proves that the vapor pressure is dependent on the chemical property of the substance. If you take water, it will be this much. If you take methyl alcohol, it will be something else. If you take acetone, it will be something else. So it will differ. Also, one thing to notice, that is independent, the vapor pressure here is independent of the amount of water taken. Even if you take 1 liter, even if you take 2 liter, doesn't matter. You will get the same value here. That is something which you should think why it is. Even if you take 1 liter or 2 liter, doesn't matter. The vapor pressure will come out to be same. But if you take methyl alcohol instead of water, the vapor pressure will be. Let's talk about solid vapor equilibrium. So we'll take the example from the iodine. So we have a solid iodine. If you see, this is a solid iodine, this is how it looks. And it sublimates substance, it sublimates easily. And this is how the gas iodine looks. Iodine gas. And this is my solid iodine. Correct. So if you see, if you keep this solid iodine in the jar for some times, what will happen is you will see this reaction happen. I2 solid, that iodine solid, will be in equilibrium. You can use this symbol, or you can use this symbol also. I2 solid will be in equilibrium with I2 vapor. Why this symbol? Because it says that the forward reaction is happening and the backward reaction is happening. We'll talk more about this symbol, right? So it says that the forward reaction happens and the backward reaction also happens. So what you do, you take a flask, empty flask, without any air, without any the iodine, pink color iodine. Just take this empty flask with a normal air and you put this iodine solid and close the lid. After some time, you see that this solid iodine will convert into gas, and the intensity of pink color will increase. It will start increasing. It will be light pink, dark, dark, dark. But after a certain stage, you see that the intensity of pink color is constant. It won't increase further. Even if you see, you'll see that some iodines are here. Some iodines, the black iodines which you have put, some are still there, but the intensity will stop increasing. See, logically, if you have more iodines, it should evaporate. It should convert into gas, right? Because there are more iodines, and it should be more darker. But that doesn't happen. After a certain stage, it stops, and that stage is called. And it exists at a given temperature. If you increase or decrease the temperature, the color of this will become lighter or darker, depending on the reactions, right? It may happen that it will become lighter and you will see some iodines here, more iodines coming in, and it may happen that it will become more darker and some of the iodines will go off from here. So it exists at a temperature because temperature plays a critical role in the equilibrium. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.